Aristotle created the first comprehensive physical theory. He tried to explain all physical phenomena within a single system based on observation and philosophical reasoning, developed the geocentric model of the universe. According to this model, the Earth is at the center of the universe and the sun, moon, and stars revolve around it. Although this model turned out to be wrong, it dominated science for many centuries. Describe the motion of bodies. Aristotle distinguished two types of motion: natural and violent. Natural motion is directed to the natural place of the body. For example, a stone falls to the ground, and violent motion is caused by an external force. He laid the foundations of mechanics and optics. Aristotle studied the laws of leverage, described the phenomena of reflection and refraction of light. Archimedes' principle. This is perhaps his most famous contribution to physics. The principle states, a body immersed in a liquid or gas is subject to an upward pushing force equal to the weight of the liquid or gas displaced by that body. This principle explains why ships float and balloons rise into the air. It is also the basis for calculating the buoyancy of any objects immersed in a liquid. Fundamentals of mechanics. Archimedes made a significant contribution to the development of mechanics as a science. He investigated levers in detail and formulated the law of leverage. Give me a fulcrum and I will turn the earth upside down. This famous phrase demonstrates his understanding of the power of the lever. Studied blocks and screws, which are simple machines to increase force. Formulated the conditions for the equilibrium of bodies. These discoveries became the basis for the development of statics, the section of mechanics that studies the equilibrium of bodies. Methods of calculating area and volume. Although these works belong to mathematics, they had a direct relation to physics as they allowed for more accurate calculation of physical quantities. He developed methods for calculating the area and volume of geometric figures such as the circle, ball, cylinder, cone, and others. His methods formed the basis of integral calculus, which appeared only many centuries later and became a powerful tool for solving physical problems. Ibn Alhazen, known in the West as Alhazen, was an outstanding Arab scientist of the 11th century who made significant contributions to the development of optics and other areas of physics. Here are some of his key achievements. Optics. Developed the first scientific theory of vision. He disproved the then common theory that the eyes emit rays of light and proved that light enters the eyes from external sources. He conducted extensive research on the refraction and reflection of light. He studied the refraction of light in lenses and other media and formulated the laws of reflection. Constructed the camera obscura. This device, the forerunner of modern cameras, demonstrated how light forms an image on a surface. He studied the anatomy of the eye. He described in detail the structure of the eye and the mechanisms by which we see. Astronomy. Developed a new theory of moonlight. He argued that the moon does not emit its own light but reflects the light of the sun. Proposed a model of the atmosphere. He took the first steps toward understanding the thickness and density of Earth's atmosphere. Copernicus proposed the heliocentric model of the universe. The main points of Copernicus' heliocentric model. The sun is at the center of the universe, not the Earth as previously thought. The Earth revolves around the sun like the other planets. The Earth rotates on its axis, which explains the change of day and night. The impact of the heliocentric model on physics. Refutation of Ptolemy's geocentric system. Copernicus' system was simpler and more elegant than Ptolemy's complex system, which required many additional circles and epicycles to explain the motion of the planets. The impetus for the development of celestial mechanics. Copernicus' model set the stage for further research into the motion of the planets and the laws governing that motion. This led to the discoveries of Kepler and Newton. A change in the view of the Earth's place in the universe. The Earth ceased to be the center of the universe, which was of great philosophical and scientific importance. Galileo Galilei. Mechanics. Study of free fall. Galileo Galilei refuted the Aristotelian statement that the speed of the fall of a body depends on its mass. He conducted experiments by dropping objects of different masses from the Leaning Tower of Pisa and proved that all bodies fall with the same acceleration without taking air resistance into account. Discovery of the principle of inertia. He established that a body on which no forces act will remain at rest or move straight and uniformly. This principle formed the basis of Newton's first law. Study of motion on an inclined plane. These experiments helped him understand the relationship between acceleration, velocity, and distance traveled. Developing mathematical laws of motion. Galileo used mathematics to describe physical phenomena, an important step toward the development of modern physics. Astronomy. Improvement of the telescope. Galileo greatly improved the design of the telescope, which allowed him to make a number of important astronomical discoveries. The discovery of the satellites of Jupiter. This discovery disproved the geocentric system of the world, as it showed that not all celestial bodies revolve around the Earth. The observation of the phases of Venus. This phenomenon also testified in favor of Copernicus' heliocentric system. Scientific method. Emphasis on experimentation and observation. Galileo believed that scientific theories should be based on empirical data. The use of mathematics to describe nature. He made significant contributions to the development of the scientific method, which is the foundation of modern science. Isaac Newton. Newton's laws of motion. First law of inertia. A body maintains a state of rest or uniform rectilinear motion until it is acted upon by an external force. The acceleration of a body is directly proportional to the force acting on it and inversely proportional to its mass. The third law, the law of action and counteraction. For every action, there is an equal and oppositely directed counteraction. These laws became the basis of classical mechanics and are still used to describe the motion of macroscopic objects. Law of universal gravitation. Newton discovered that all bodies in the universe are attracted to each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This law explained the motion of the planets around the sun, tides, the fall of bodies on the Earth, and many other phenomena. Optics. The decomposition of white light. Newton conducted experiments with prisms and showed that white light consists of a spectrum of colors. Development of the corpuscular theory of light. He believed that light was composed of tiny particles, corpuscles. Although the wave theory of light was later developed, the corpuscular theory also proved to be true in certain cases. He constructed the first reflecting telescope. This invention avoided the chromatic aberrations inherent in lenticular telescopes. Mathematics. Developed differential and integral calculus. This is a powerful mathematical apparatus that has become an indispensable tool in physics and other sciences. Michael Faraday. Electromagnetic induction. Faraday discovered the phenomenon of electromagnetic induction, which formed the basis of modern electric current generators. He proved that changing the magnetic field around a conductor generates an electric current in it. Laws of electrolysis. Faraday formulated the laws of electrolysis, which relate the amount of substance released at the electrode to the electric charge passed through the electrolyte. These laws are used in electrochemistry and electroplating. The concept of electromagnetic field. Faraday introduced the concept of lines of force and the field surrounding a magnet and electric charge. This concept proved to be key to understanding electromagnetic phenomena and became the basis for Maxwell's work. Diamagnetism. Faraday discovered the phenomenon of diamagnetism, the property of matter to weaken the magnetic field. He showed that diamagnetism is inherent in all substances, although in different degrees. Experiments with electricity and magnetism. Faraday conducted many experiments that helped him make his discoveries. He developed various devices, including an electric motor and a transformer. James Clerk Maxwell. Maxwell's equations. This is a system of four equations that describe all electromagnetic phenomena. They combine electricity, magnetism, and light into one theory. Maxwell's equations are one of the most important advances in the history of physics. Prediction of electromagnetic waves. Based on his equations, Maxwell predicted the existence of electromagnetic waves propagating at the speed of light. This prediction was later confirmed experimentally by Heinrich Hertz, leading to the development of radio communication. Kinetic theory of gases. Maxwell made significant contributions to the development of the kinetic theory of gases. He derived the velocity distribution of gas molecules' Maxwell distribution, which is an important tool in statistical physics. Color photography. Maxwell obtained the world's first color photograph in 1861 using three colored filters: red, green, and blue. Control theory. Maxwell also worked on stability problems of control systems and developed theoretical methods for analyzing stability.